In this video, we are going to take our design from the previous video and improve it so that it's optimized, so that it uses less registers and it uses a smaller adder, which will make it faster. So let's take this design from our previous session and think about how we can improve it. Let's assume you wanted to do a multiplication of a 64-bit number by a 64-bit number. To be able to do it, you need a 128-bit register here. You need another 180-bit register here for the product. And you need a 128-bit adder. Now, a 128-bit adder is not so easy to create. And these are going to take a lot of space. Okay, so let's think through what this algorithm does. What it does is going to start by setting p to 0. In the next round, it's going to add to it a multiplied by b0, right? In the next one, it's going to add to it a multiplied by 2, so twice a multiplied by b1. Why twice a? Because we are shifting a to the left. Why b1? Because we are shifting b to the right. Okay, so whenever you shift something to the left, it's as if you are multiplying it by 2. Then in the next round, it's going to set it to, it's going to add to it 2 to the power of 2, because we shift one more time, b2, and then 2 to the power of 3, b3. That's what this algorithm is computing, sort of starting from here, iteration 1, iteration 2, iteration 3, and iteration 4. Now, I'm going to just take this and think about if I can rewrite it mathematically in a different way. What if I start by setting the value of p to 16 times ab0, then, so I'm going to call this, I don't know, p0, for example. Then I'm going to divide the previous p by 2 and add to it, again, 16 times a b1 this time. Then I'm going to take b2 and set it to p1 plus 16 times b2. P3 is going to be P2 divided by 2 plus 16 times AB3. And P4 is just going to be simply P3 divided by 2. Okay. Now, if I do this, what is the final value that I get for P4? You should just replace, P3 here, P2 here, and if you just keep doing these replacements, you are going to see that we are going to have, for example, 16 times AB3 over here divided by 2. So that will give you 8, which is 2 to the 3 times AB3. We are going to have 16 times AB2 divided by 2 once here to get the P3, and then once divided here again by 2 to get P4. So it's going to get divided by 2 twice. So instead of 16, which we started with, it's going to have a multiplicand of 2 to the 2, AB2. Similarly, for AB1, it's going to be 2AB1. And for AB0, it's just going to be AB0. Right? You have 16 times AB0. It gets divided by 2, 1, 2, 3, 4 times. You just get AB0 at the end. So this calculation also gives me the correct value. You can check that these two values are exactly the same. Okay, so what does this algorithm, what does this calculation suggest? What algorithm could accomplish this? Imagine that you will still have your register P, you will still have your register A. Remember that register A was M bits. I'm going to divide P into two parts. Its most significant M bits and the less significant N bits. And we also, of course, have B, which is going to be N bits. Now, if I want to implement the algorithm I have done there, I still need an adder. But there is something very interesting now. Each time we are adding something with 16AB0, 16AB1, 16AB2, and 16AB3. So if I keep shifting B to the right in each iteration, all I need to be able to do is take the least significant bit of B, and depending on whether it's 0 and 1, either add A or 0, shift it to the left. Why did we have 16 here? 16 is a sort of equivalent of what we call 2 to the, is 2 to the 4, which is 2 to the n here, right? So what if I just take A and add it with only this most significant part of P? If I do that, that's as if we first multiplied A by 2 to the n, because it's like A was shifted n bits to the left and then summed, right? So what we are going to do is just take these bits and add them with the most significant part of P, the most significant n bits of P. We get a result, and that result can go back into the product. Now, before we move to the next iteration, so this was the first iteration, each time, look what happens here. We sum the previous one divided by 2 with our new result, right? Before we add these new results, we need to divide the previous results by half. So I have to shift the product to right. This becomes an implementation of the new algorithm, right? And we have this new implementation in your slides right over here. Okay, so this is just the same thing drawn again. You have your multiplicand, you have your multiplier, right? So in this example, if you have 64-bit numbers, you are going to need only a 64-bit register here, a 64-bit register here. You will still need the 128-bit register over there, but your adder has become 64-bit. And a 64-bit adder is going to be faster than a 128-bit adder. So our design is a little bit improved, both in terms of the amount of registers it needs and in terms of its running time. Now, there is one more improvement that we can make to this design, and that improvement is this. See how we take this multiplicand and we just always, we take this multiplier and we always shift it to the right. And we do the same exact thing with the product. Both of these are shifted to the right. And remember that we are always just adding stuff to this part of the product, not the least significant part. So there is another the simple optimization you can do. What if I just take this multiplier here and just move it and save it here in the product to begin with? Because we are going to shift right each time, eventually all of the multiplier is going to go out. But if we do this, we are saving one more register. We don't need a register for the multiplier.
and we don't need to shift right both the product and the multiplier. So this is the design that will result. This is sort of the most optimum design we can come up with this sort of simple algorithm for multiplication. Okay, so at each point in time, you just look at the least significant bit of your product and you decide whether you want to add the multiplier or a zero, right? So you can always just add a multiplexer. You get a completely functioning multiplier if you do a design like this. In the class, what we are going to do is we are going to go through an example of how it would work.